Hey guys, welcome to the Expert Audio channel. This is normally going to be a live show, but I figured for once, just to see how my editing skills and so on, I will do something offline here. I get asked for monitor controller DACs pretty often, believe it or not. You know, monitor controls are a pretty cool thing to have in the studio these days. Mixing consoles are really going away a lot more. People are doing more in the box, but they also want the ability to do local volume control and switch different sources and so on. And one of the things I get requested is a monitoring DAC, so they can bring USB audio or SpeedIF audio from their system and you put it through a DAC to analog outputs. Now, first thing I do whenever somebody asks me is I have a look on Aliexpress first, just to have a look at what I'm competing against and how I can do better than them. And so what we're looking at here is a small board that I got on Aliexpress. Let's see if I can find the link here. And here you can actually see the board itself. So there's a microscope as well. So this was $5 delivered, which is pretty amazing if you ask me. And what we're looking at here, it's a pretty simple board in many ways. Let's see if I can take this higher. No, that's going down. Okay, so what you gotta know about my microscope is that it's very manual, okay? You have a pair of RCAs on the output here, so this is a single-ended output. You have digital input over here, so this is a bit clock, data, left, right clock, ground, VCC, and again, no documentation for this, so we're actually going to kind of reverse engineer a little bit what it's going to take to get this device up and running. It looks like we've got 3 regulators of some kind. These look like, let's see if I can zoom in manually, AMS111733s. Let's have a look here. There we go, AMS1117. One there and one there. So these are, I've already done my homework on this. These are 3.3 volt regulators. Okay, and we'll look into these a little bit more. So we can assume the device in the middle is 3.3 volts. And because I kind of know this device, this DAC that's in the middle, this is a 2 volt RMS DAC. So it's a DAC that was created. I worked on this. This is my DAC from TI. It's quite nice. I found an AliExpress board for it. It's cheaper than the evaluation board. But this DAC, when I was working on it, really was designed for 2 purposes. One, high performance. So this one offers up to 112 dB dynamic range. But also, the aim was to make it really as easy as possible to people to design in with. So before this, for instance, with DACs, you had to have external pop and click circuits to avoid them. You also had high voltage rails on the output, so you needed op amps on the output to make it a balanced, not only balanced, but a bipolar output, so it was ground biased and so on, because otherwise you have pops and clicks with DC. But also things like clocks and stuff are a major pain. Traditionally you had master clock, bit clock, data, and left-right clock. So your left-right clock's easy to source, your bit clock is there with your data, but master clock is typically different for every DAC, and so you end up needing sort of 256 or 64 or 128 times your left-right clock to get there, which is a real pain. In addition to this, a lot of DACs out there in the market, a lot of the higher performance ones, needed custom configurations based on your sampling rate. So if your sampling rate was 48 kilohertz, you had to change certain pins a certain way, and if it was 96, another. If it was 192, different again. You would be amazed how many receivers out there cannot tell. They just lock onto a new signal and they don't tell you, they don't give you bits to control in a microcontroller or anything like that to tell you what the sample rate is. So in the 5102, we put all of that in there. It's basically an automatic gearbox of a device, and so it's one of the reasons why it's become so popular in devices like Raspberry Pi systems, because you don't actually need to know what the sample rate of the data coming in is, and you don't have to give it a master clock either. You just give it a little bit of bit clock, left, right clock, and data, and off it goes. It'll even also do the automatic muting and so on, and gentle muting if you suddenly lose clocks or suddenly lose data and so on. So let's dig in a little bit deeper here to see the implementation done by this person on Aliexpress. I think that's going to be pretty interesting. Alright, so pin 1 is just up here, you can see it by the dot there. And let's see if we can improve the view a little. There we go. Alright, so there we go, look at that, beautiful. Okay, so let's have a look at the datasheet here. I'm going to pull up the pin out, so let's scroll. And pin out, and I'm going to zoom in a little bit to make it easier for those following at home. Alright, so CPVDD is a charge pump pin. CAPP is going to be your switch cap, again for the charge pump ground. The other thing I want to point out here is when I was at TI, we spent a lot of time working on the division of kind of boundaries of areas on the chip. So for instance, you'll see up here, these 4 pins are all your charge pump areas, and the VNEG that comes out. Out L, out R, analog VDD, analog ground, these are your analog output pins. So these are kind of sensitive, you don't want any like clocks and things like that crossing near these. This deemp pin is a de-emphasis pin. It's a single pin that you either pull high or low. So there's no like clocking or fast clocks, fast signals going on here. Over here, this is the filter pin where you select whether it's a IIR or FIR pin. This is your digital clock interface, and again, this is going to be very fast stuff going on here. So SCK is running at 6 megahertz or so if you have it in the system. BCK is going to be running at 64 times your sampling rate. So if you're running at 48 kilohertz, it's going to be running at 64 times that, or 128. This is your digital input pin, so this is going at 64 times your sampling rate. LRCK is going to be a sample rate like 48 kilohertz, 96 or 192. FMT is a format pin, so that's going to be pulled high or low, and it tells the device whether it's getting left justified data or I2S data. XSMT, I wonder if they did anything with this. This is a pin I actually fought pretty hard for. This is a pin that you tie it to something slightly lower than your power supply, slightly lower than your 3.3 volt power supply, so that when it crosses a threshold, the device starts auto-muting before the power rail is completely lost. LDO out, this is going to be for your digital supply. So internally there's an LDO, a power regulator that takes 3.3 and makes it, I think it was 1.8 to 1.6 volts, and that's used internally by the digital core to make sure to run lower voltage and higher speed. And then you've got 2 power rails here. Again, this is DVDD 3.3 volt and DGND digital ground. Now on this device we kind of treat ground as one complete entity. It's often easier to do that, but what we'll do is we'll actually control, or in our layout we'll partition kind of high-speed clocks and digital signals away from the analog. So you almost have a division straight down this device, or in fact you probably have something that's kind of taking 3/4 of this device and keeping those noisy signals over this way, and then your analog signals over this way. And you can see that's actually been done here as well. So let's start going around the device to see if I can catch a little bit of extra focus. Gosh, times like this I wish I had a better microscope. But you'll see here there are 2 470 ohm, 470 or 447 ohm outputs, and then 2.2 nanofarad caps, and these set up here. So there's 470 ohm. You can see it written on the silk screen here, 470 and 2.2, and these create a low pass filter and also isolate the output from any capacitance and so on. So those are these 2 pin, out L, out R. But let's start from the top. I should really start from the top, shouldn't I? So we have CPVDD, and you can see here that's that has this cap to ground from the looks of things, and this tantalum, just a minute, and that's actually coming, that has its own regulator, that's this AMS1117. So charge pump VDD on this PCB is running from the AMS1117. On the other side of the board we have exactly a mirror, right, for DVDD. So DVDD is here, and that's actually that has a local cap here, and then also another tantalum, and it's getting its supply from an AMS1117 as well. So it looks like whoever's designed this board has actually decided to drive it with 2 separate regulators, which pretty useful, to be fair, although I do wonder, you know, this device, the charge pump is pulling at a pretty high rate, high frequency, so it's going to be pulling current in at a pretty high frequency. I do wonder if this regulator can keep up, but some of that's been isolated by these capacitors here. So there's your, they've used a 2.2 microfarad here, because once you start using a certain specific value of cap, you may as well just keep on using it on the entire board. For the charge pump ground and charge pump negative, they've actually, for VNeg, so 1, 2, 3, 4, 5. So pin 5 and ground is your VNeg. So VNeg is being isolated with a being power supply decoupled with a 2.2 microfarad cap. You've got your outputs by here, and then we're on to A VDD, A ground, and D amp. Well, now then, that's interesting because I don't see a cap here, but if any of the rest of the board is anything to go by, it looks like these two caps are likely connected to pin 8. Why don't I get a scope and just measure that real quick. Where's my? These 3 traces are all connected, so I'm going to put my stubby one by there. See if I can see pin number 8. You can hear that pretty well. Let's see if I can. So pin number 8 is obviously connected here, and it's getting a feed from another AMS 1117. So I think I could almost start drawing this out, to be honest with you. So let's keep on going around the board. It looks like they've grounded D amp. So why don't I look at what the settings are for that? De-emphasis off. So de-emphasis, for those of you that don't know, the old CD players, the very early CD players, the A to D converters that they were using didn't have a linear response, and so what they actually had to do was digitally, when they were playing it back, add the right response back in. It's very similar to the old RIAA filter that we used for vinyl years and years and years ago. And so here we want it off or on. Ideally we want it off for most of the CDs that we listen to. They're very early CDs that actually had a setting where you could switch this on, but for most of the stuff that we listen to these days, it's all off. Anything recorded in the last sort of 15-20 years, in fact, 1990 plus, is going to be without de-emphasis. So, but it's there because we had to put it in because a customer demanded it. We won't name and shame who. Filter in this case, you can see this pin, which is pin 11, I believe. I'm going to use a pencil to point for now. Pin 11 here looks to be grounded as well. You can just see this little stub of a trace by here. So pin 11 FLT, and I believe, yeah, there we go. So pin 11 here, this is on normal latency. That means it's an FIR filter, not an IIR filter. FIR filters have a slightly longer response time, but the output is way more linear in terms of amplitude over frequency, and it has a sharper roll-off as well for its low-pass filter. So it's preferred for music playback. Typically, if you're doing pro audio stuff where latency is critical, you'll sacrifice that linearity for lower latency. So in the board that I would design, that would be something I'd probably put onto a jumper to allow the end developer to use. From there, we've got a couple of resistors here for BCK data and LRK. Not really sure why they put these in here. Probably just to slow down some of the reflections and so on. It's good practice to put them in, and resistors are more or less free these days, so I've got no qualms with also doing that as well. Once we've gone beyond a BCK, let's go back up we've gone, so let's count up our pins here. We've got a filter there. SCK has been grounded as well, which is going to put this device into PLL mode, so it generates an internal SCK for itself. From there we've got bit clock, and I'm going to marry them here. So bit clock, data, left right clock, that's LRCK, and then we've got the format pin, Now the format pin in this case has been brought up to a jumper. You see that? This jumper up here? Let me spin the board around now so you can see it. There's a format pin which goes to I2S and left justified. I2S and left justified, so you can select there what, depending on the source you have, depending on, you know, you'll typically have a USB chip or a speediff receiver, and you'll set the output on that whether you want it I2S or left justified. There are folks that use right justified out there. I think Sony used to use a lot of right justified stuff. They always have to be a little bit different, didn't they? Now I'm interested in seeing what they did with XSMT here, because as I said, normally you'd put that through a potential divider and set it just above a threshold, and I think the threshold on this device was like 2 volts. So you would set your potential divider so that the top of it would be 3.3 and the threshold would be 2.2 or something like that. So if 3.3 ever dropped, the 2.2 would drop through the threshold faster, and you would start auto muting, so that by the time the device browned out, you would already be muted and tied to ground. So let's have a look at that. So we've got format. Let's have a look. Here we go. Spin it the other way around now. We've got, I'm going to move this again. Okay, good. Okay, so we've got the LRCK is coming in from this resistor. So it's LRCK. The next one up is going to be format, and then the next one is XSMT. So I wonder what that's connected to right now. The next one is going to be LDO out, which is going to a cap, as it should be, cap to ground. And then the one after that is digital ground, which I suspect is being taken under the device. And then this here is off to our DVD. So the next question is, what is XSMT hooked up to? Did they put it into some kind of potential divider? I don't see it, so I suspect it's actually connected to a DVD. Let's have a quick look. XSMT, and look at that. So they've connected that directly. They've connected that directly to the DVD pin. So what would I do different there? So one of the things I do is probably either firstly connect that through a potential divider so it auto mutes, but also I can hook that directly to a mute pin on my product. D, V, D, D. This is going to come into a resistor, and this comes to ground, and this is going to go off to the XSMT pin. Yes? Okay. So what I'm proposing to do is add these, and with the appropriate values, but also add a switch here. So here's a mechanical switch that I can use to mute the output of the DAC very, very quickly. And by doing this, I think it's actually going to be a more elegant mute circuit than, I'll put a cap here as well, just to take the edges off. It'll be more elegant to do it that way than it will to use relays or anything like that. So you'll be able to push here and it'll drop the signal very, very quickly. Now worst case, if I do use an external switch with relays for other things and so on, the other thing I can do here is actually replace this with a simple NPN as well. So but essentially what we'll do is we will short, let's go from here over to here and here. Make sure this is okay, and we'll be able to short out the signal. So, other than that, let's go back to the pin here, microscope and browser. This is a nice little device. This nice little DAC. 112 dB is going to give you, 16 dB of attenuation before you even have to lose any 16-bit quality. So it's going to be, most of the signal is going to be lost in noise anyway in the rest of your system. But the nice things about this device, no need for a master clock, no need for any brains to reconfigure it. So if you change from 48 kilohertz to 96, this device just knows what's going on. Really, really nice like that. And other than that, it's a nice little device that auto mutes and everything else as well. So no wonder it's been so popular with the Raspberry Pi crowd and so on, because they just never know what's going to be coming out of their media players. So nice things in this implementation is the use of these AMS 1117s for each of the power rails, and nice big caps next to each of them. I'm not sure if he needs to have tantalum caps everywhere. We could probably just use aluminum electrolytics if they're cheaper. There's no major benefit there. What power supply? Now remember, there's no documentation that comes with this board. We have a VCC here. So this device needs 3.3 volts to operate. So I'm going to go to the AMS1117 datasheet here, and for those of you that have experience in this, you're probably already yelling at the screen going, "No, it's this, what's wrong with you?" But here we go. This is the clue right here. So this is a 1 volt dropout, which essentially in a regulator means that if you want 3.3 volts, you need at least 4.3 volts. So you need, it needs that kind of headroom. We can drop out voltage. So here's your dropout voltage, V in to V out, you see? So you need, worst case, 1.3. So 3.3 plus 1.3 is 4.6. So you're looking at like a 4.6 volt, kind of to be safe minimum. So if you got a 5 volt supply, boom, this part's going to be great. It's going to do exactly what you need. This device doesn't pull a lot of current, so these regulators aren't going to get too hot. The other thing, and now that I mention it, is DVD. Let's go back to the top down. So hand base, there we go. This probably doesn't need to be DVD. We'll probably add this to the 5 volt rail, because typically in the system you'll have. It's a pity this is so poorly focused. I'm going to work on that. You'll typically have your 5 volt rail. That's going to your AMS1117. Right, this has a cap, this has a cap, and then this is going to be your DVD rail. So ideally, if you lose this power supply, you want this one to drop. You want this one to drop the system, because this has to discharge, and then this will discharge before DVD discharges. Browns out the 51XX, right? So you got 51XX over here, and this is going to go. Today this is going to go into XSMT. Well, you know what? Let's hook that in over here through a potential divider instead. So when this drops to XSMT, it'll mute out. So good luck, folks. I'm probably going to use a PCM5102 for this design. I'll actually talk about that a little bit more a little bit later. Until then, good luck, and let me know in the comments below. Don't forget to smash like and subscribe and all that kind of nonsense. Your feedback will be awesome. Thank you. Bye bye.